Ever try explaining what chocolate tastes like to someone who's never even had a bite?
Yeah.
It'd be like, I don't know, trying to describe colors to someone who's been blind since birth.
Right.
Like, where would you even begin?
Yeah, that's a good point.
Turns out teaching computers to understand words, well, used to be that difficult.
Yeah, you're right.
It's a real challenge to get computers to grasp all those little nuances of human language.
It really is.
They used to process words, well, kind of like robots reading a dictionary,
I see what you mean.
recognizing the letters but completely missing the subtle shades of meaning that we humans pick up on without even thinking.
It's true. For a long time, computers just couldn't quite grasp the deeper meaning behind words. They were just strings of letters, devoid of the richness and complexity of human language.
It's like that time my phone tried to autocorrect, "I'm feeling under the weather," to "I'm feeling under the leather."
Okay.
Not exactly the same message, is it?
Not quite, no. And that's why the development of something called word vectors was such a game changer in this field.
Word vectors. Okay, now those sound intriguing.
Yeah.
Tell us more.
Imagine if you could give every single word its own special code, a set of coordinates, like on a map, that places it in this vast, multidimensional landscape of meaning.
Hold on, multidimensional landscape.
Yeah.
That sounds like we're about to enter the Matrix here. Maybe you could maybe break that down a little bit further for us.
Sure. Okay, so imagine this.
Okay.
Each word is like a star in space, right? Words with similar meanings, they're like stars clustered together in the same constellation, while words with opposite meanings, well, those are light years apart.
So the closer they are in this like meaning map, the more related they are.
Exactly. And that's really the beauty of word vectors.
All right.
They let computers actually see these relationships. So a computer can understand that king is to queen as, say, man is to woman.
Wow.
Even though those words themselves, they look totally different.
That's wild. But this whole meaning map thing, it's got to be incredibly complex.
It is. It is.
How do they even go about creating these word vectors? Like, where do you even start?
Well, there are a bunch of different models, and each one has its own approach.
Okay.
You might remember us talking about NNLM, the neural network language model.
Vaguely. It rings a bell, but maybe refresh my memory. What was that one all about again?
So NNLM, that was an earlier attempt at creating word vectors.
Oh!
And it worked. But it was kind of like, using a supercomputer to calculate a simple sum. Effective, yeah, but not very efficient.
So it was a bit of a gas guzzler in the world of language processing.
Exactly. And that's actually where this research paper we're looking at comes in. They introduced these two new models, CBOW and Skip-gram.
CBOW and Skip-gram. Those names sound like something out of, like, a Dr. Seuss book or something.
Right.
But I'm guessing they're a little bit more streamlined than that NNLM thing.
Yeah, you bet. These models, they were designed for speed and efficiency.
Okay.
So CBOW, which stands for continuous bag of words.
Catchy.
It tries to predict a word based on the words around it, kind of like filling in the blank in a sentence.
So if you gave CBOW the sentence like, "The blank barked at the mailman," it could figure out that the missing word is probably dog.
Exactly. You got it.
Huh.
And the Skip-gram model, well, that one works kind of in reverse.
Okay.
It takes a word,
Okay.
and then it tries to predict what other words are most likely to show up near it.
So if you fed it coffee, it might spit out cup, hot, caffeine, that kind of thing.
You got it. You're exactly right.
Okay, cool.
And the really cool part here is that both CBOW and Skip-gram, they're just way faster and more efficient than NNLM.
Okay, so they're efficient.
Yeah.
But how does that translate to better word vectors? Like, what's the big deal about speed?
It's all about scale.
Okay.
So with these more efficient models, researchers, they can train those word vectors on absolutely massive data sets. We're talking billions and billions of words.
Wow.
And the more data you can feed those models, the more nuanced and accurate those word vectors are going to be.
So it's like the difference between like learning a language from a phrase book versus like actually immersing yourself in a foreign country for a year.
That's a great analogy, yeah. And you know what? This leads to some really impressive results.
Oh, okay.
Remember those tables from the critique we talked about?
Yeah.
That's where things get really exciting.
So before the break, we were talking about CBOW and Skip-gram being able to process tons of information.
Right. Huge amounts of data.
But data without results, it's like a library with no books.
Exactly. It's all theoretical at that point.
So how do we know if these word vectors are actually any good?
Well, that's where the researchers got really clever. They designed a test based on analogies.
Analogies, okay, like those brain-bending puzzles we used to do in school.
Yeah, exactly.
So instead of shoe is to foot as glove is to, they'd give the model something like France is to Paris as Italy is to.
You got it. And the idea was to see if these word vectors, after being trained on this massive amount of data, if they could actually figure out the relationships between words.
Okay, and what happened?
Well, the results were astounding. They really were.
Okay, I spill the tea. What kind of results are you talking about?
Well, in one of the tests, and you can actually see this in Table 8, they gave the model France, Paris, Italy.
Okay.
And it correctly predicted Rome.
Wow, okay. That's seriously impressive. Like, it actually got that.
Yeah, it did. And it gets even better.
Okay.
It also aced these trickier relationships. Things like big, bigger, small, larger.
Oh, really?
Yeah, we're talking over 80% accuracy on these complex analogies.
That's incredible.
I know. It really shows you just how powerful these models can be.
It's like, it's not just memorizing definitions anymore. It's actually understanding, like, the underlying concepts.
Right, exactly.
This feels like a giant leap forward for AI.
It really is. And if you look at Table 4, you'll see the actual numbers that back it up. You know, this isn't just like a fluke or anything.
Yes,
it's demonstrating this deep understanding of how language actually works.
This has to have some pretty massive implications for the future of technology, right?
Absolutely. I mean, think about it. Imagine what this could mean for things like language translation.
Okay.
You're making it way more accurate and natural sounding.
Right. That would be huge.
Or what about searching for information online? These advancements, they could lead to search engines that understand exactly what you're looking for.
Instead of just matching keywords.
Exactly.
It's like we're on the verge of finally breaking down the language barrier between us and machines.
Right. It's pretty exciting.
Yeah.
And, you know, even though these models are already doing some incredible things,
yeah,
the researchers, they still think there's room for improvement.
Always pushing the boundaries. I love that.
That's how progress happens, right?
Exactly.
So one area where they see potential for improvement is incorporating even more information about the structure of words themselves, you know.
Okay, so like prefixes, suffixes, root words, that sort of thing.
Exactly. Like taking cues from good old-fashioned linguistics. And then, of course, there's always the quest for more data. I mean, we've seen it time and time again.
Yeah.
The bigger the data set, the smarter these models become. Who knows what they'll be capable of with even larger data sets to learn from.
That is a thought-provoking question to leave us with.
There you go.
We've gone from computers struggling with basic definitions to them solving these complex linguistic puzzles, and with incredible accuracy.
It's pretty amazing when you think about it, how far we've come.
It really is. This deep dive has shown us just how far we've come in teaching computers to understand the complexities of us, of human language, and it leaves me wondering, like, if computers can do all this now, what will they be capable of in the future?
The possibilities are endless, really.
That's all the time we have for today's deep dive into the fascinating world of word vectors. We'll see you next time when we'll explore another cutting-edge topic. Until then, keep those algorithms humming.